Welcome to Exact Education. The purpose of this video is to explain semiconductor components. The base component of all semiconductors is the p-n junction, or commonly known as a diode. A diode is an active component. What do we mean by active? It requires a source of energy to provide its proper function. It needs to be biased with the appropriate DC power. Unlike passive components such as resistors and capacitors that simply convert or store energy. Keywords we're going to investigate: semiconductor material, doping, p-n junction, diffusion, depletion layer, and the barrier potential. If we take semiconductor material such as silicon and we dope it, we inject foreign material such as phosphorus, we create a negatively charged material where there's a surplus of electrons. If we dope silicon with boron, we then have a deficiency of electrons or holes. Silicon on its own is neither a good conductor or a good insulator. It has little electrical use in its pure form. However, if we dope it, we then create N-type and P-type material. If we bring those two materials together across that junction, we form a junction diode. So how does a junction diode form? We get the process of diffusion. As we bring N-type and P-type materials together, the electrons and the holes merge across the junction. As a process of diffusion, as they merge, an electrical field is built up. And as that electrical field grows, it limits and eventually ceases the process of diffusion. And what we then create is a balanced system where we have a depletion layer across the junction, which provides an internal electrical field. How do we use this component? What we do is we bias it with a voltage greater than 0.6 volts, whereby we can get conduction in one direction and no conduction in the reverse direction. So if we forward bias the device, the voltage 0.6 volts and above, we can get conduction through the device from the anode to the cathode, forming a low resistance path. If we reverse bias the device, then we have no conduction. We have formed a one-way electronic switch. So if we, for example, apply a battery plus side to the anode, to the P side, positively charged side, negative terminal of the battery to the cathode, the negative charged side, if we provide a large enough voltage above 0.6 volts, then we have current flow through the device, provides a low resistance one-way path. If we form a current loop through a diode, resistor into a battery, we can get current to flow in one direction. So one particular use of diodes is in rectification power supplies, where we want to convert mains AC to low voltage DC power supplies. And if you've ever opened up one of those power supplies, you can see 4 diodes in a ring, which forms a bridge rectifier. The diodes operate in pairs such that the current only flows in one direction through the load, and we've created a DC power supply, AC into a bridge rectifier, DC out of the bridge rectifier. If we look at current versus voltage characteristics of a diode, if the voltage is 0, there is no conduction through the diode. As we increase the voltage to approximately 0.3 volts, then we get to the cut-in voltage, and the diode will start to conduct in a non-linear fashion through this region here. Once we get above the on voltage, above 0.6 volts, then we get into the linear region of the diode, and it will conduct as a low resistance path of approximately 20 ohms. If we reverse bias the diode, eventually the material will break down and it will conduct with large currents with tiny voltage change. When we get up to this stage here, we can manufacture deliberately what we call Zener diodes, which are designed to operate in reverse. And those Zener diodes are used in DC power supplies to clamp the DC voltage in reverse. So for example, if you want a 5-volt power supply, then you would probably choose maybe a 6.2 volt Zener diode to clamp the voltage and provide a stable power supply voltage no matter what the current is drawn by the load. So when we get to 0.3 cut-in voltage, diode starts to conduct in a nonlinear fashion. Above 0.6, we get into the linear region, and the on resistance of the diode, we can measure that by taking the change in voltage divided by the change in current, as in Ohm's law. If we connect two diodes back to back, we create a 3-pin device. So what would be the function of a 3-pin device if we connect diodes back to back? We then form 3-pin device, base, collector, emitter. Two ways we can operate this device. We can operate it as a small signal amplifier. We put small current into the base. Any change of current in the base is reflected by a large change in current on the collector side, whereby we create signal amplification. The other way to use a transistor is an electronic switch. The base is the control pin, and if the transistor is fully switched on in saturation mode, whereby you cannot get any increase in collector current because the base is fully switched on, then you create a low resistance path between the collector and emitter. Effectively, the switching pins are the collector and emitter. If we switch the base off, then the collector and emitter are electrically isolated so that we create an open circuit, whereby we create a digital switch. The advantage of semiconductor components is that you can miniaturize diodes and transistors onto silicon wafers. So nowadays in mobile phones, laptops, 64-bit word machines, we literally have billions of transistors etched onto silicon chips, and we can have massive processing power, as in digital computers.